Now, one of the things we're really curious about when we do regression is asking the question, is there actually a linear relationship between these two variables? That is it realistic for us to use one variable to predict the other one? To answer this question, we really need to look at where the regression equation comes from, specifically where the slope comes from. Because slope tells us that for each step over an x, how many does our y variable change by, either positive or negative. Now the equation of our slope is b1 is equal to r times sy over sx. We know that r measures the strength of an association, specifically the strength of a linear association, and so let's talk a little bit about what r is. Well, we know that if r is positive, then that means our variable as x increases, y increases, or as x decreases, y decreases. We know that if r is negative, it means as x decreases, y increases, or rather as x increases, y decreases. That is, one gives us this nice association, that is a positive association, the other gives us this association that's kind of inverted, what we call a negative association. So r controls whether or not our slope is positive or our slope is negative. There's something else r can tell us, and that is we know the larger the r value, that is 1 or negative 1, the stronger the linear association is, which means the smaller the r value is, the closer it is to 0, the less power that relationship has. An r value of exactly 0 means we have no linear association. And what this tells us is that if we look at our slope, there are only so many different ways that our slope could actually be equal to 0. For instance, maybe we have a standard deviation of y equal to 0. Well, this would mean that all the y values were exactly the same, and that's not really going to happen in real life data, so sy probably not equal to 0. Sx, well, Sx equals 0 wouldn't cause our slope to be 0, it causes our slope to be undefined, and once again, standard deviation equal to 0 would mean x would have all the same values, not likely to happen in real life data, so we can throw that out as well. Which means if our slope is 0, well, sy can't be 0, sx can't be 0, that must mean that r is equal to 0. In this way, r equals 0, having no linear association, gives us a slope of 0, which allows us to test something really, really important. While b1 is unlikely to be 0, that is, the slope we get from our sample is unlikely to be equal to 0, in some cases, our slope is actually going to be very, very small. And so, while it may look like a change in x results in a change in y, it's always worth investigating if this change would actually hold if we went from our sample over to the population. Because we want to test if there's a linear association, we're going to be testing beta 1, the population parameter that goes with b1, our sample statistic. And we'll be testing if beta 1 is equal to 0. Beta 1 equal to 0 implies that r is equal to 0, which would tell us that there's no linear association. That is, our variables look like they may be independent of each other. We'll be testing beta 1 equals 0 against the idea of beta 1 not equal to 0. If beta 1 is not equal to 0, that must mean that r is not equal to 0. And if r is not equal to 0, that means there's a linear association between our variables.